Hey everyone, welcome back to Astrum Sleep Space. Today, we're diving into a truly mind-bending mystery that's been puzzling scientists for decades. Imagine this: a radio signal coming from deep space every 22 minutes, without fail, for the last 35 years. What could it be? Is it a natural phenomenon? An advanced civilization reaching out? Or something we can't even imagine yet? In this video, we're exploring the origins, theories, and possibilities surrounding this incredible discovery. So, get comfortable. Let's go on a journey to the edges of science and imagination. In 2022, astronomers using the Murchison Wide Field Array made an astonishing discovery: a mysterious new radio signal that seemed to pulse every 22 minutes. At first, this didn't raise too many eyebrows after all. Astronomers are familiar with repeating signals from pulsars, which are rotating neutron stars that emit powerful bursts of energy. But as they combed through decades of past data, they uncovered something surprising. This signal had been consistently reaching Earth since at least 1988, with an unusual and striking stability. If this signal was coming from a neutron star, it wasn't like any they'd encountered before. Pulsars typically slow down over time, but this one appeared to be rotating with unchanging precision every 21 minutes and 58 seconds. Where was this signal coming from, and what could produce such a steady pattern? Hi, I'm Alex Mullen, and welcome to the Astron podcast. Today, we'll dig into the mystery behind this enigmatic signal, a discovery that challenges what we thought we knew about some of the most awe-inspiring objects in the cosmos. The source of the signal, named GPMJ 183910, is located about 18,000 light-years from Earth. The signal arrives as pulses lasting anywhere from 30 seconds to 5 minutes, and each pulse can show up within a roughly 6.5-minute window around that 22-minute mark. At first glance, this may not seem particularly steady after all. 30 seconds and 5 minutes are vastly different durations, and the variability in pulse arrival times doesn't suggest a stable source. But the dynamics of neutron stars are complex, and many factors could affect both the duration and timing of the pulses we detect. By analyzing data from the past 35 years, astronomers managed to isolate this signal from all the background noise, averaging out the natural fluctuations. To their astonishment, they confirmed that the source's rotation period has remained steady for over 3 decades, something almost unheard of in neutron stars, which usually slow down over time. So, what could possibly explain this strange, unwavering signal? Join us as we explore the theories and the profound questions they raise about our universe. As this object radiates energy into space, astronomers have calculated that if it has slowed down at all over the last 35 years, its rotation period could only have increased by a minuscule 0.28 milliseconds. That's such a tiny change that it would have gone undetected in our data. This incredible level of stability is almost unheard of. Whatever this object is, it's spinning with astonishing precision. Pulsars, often referred to as the cosmic clocks, typically rotate with impressive consistency. They're so steady that we use them to keep time over enormous cosmic distances. But here's the twist: for a pulsar rotating this slowly, such stability is highly unusual. To understand why, let's dive into what makes pulsars tick and why they usually slow down over time. Pulsars are neutron stars, the dense remnants left behind after supergiant stars explode in supernovas. Aside from black holes, neutron stars are the densest objects in the universe. Imagine a star so dense that every atom has collapsed, leaving no empty space. Regular matter, like the atoms in planets or people, is mostly empty space. Over 99.999% of an atom is just the gap between its electrons and nucleus. But in a neutron star, that space is gone. Picture something so dense that a teaspoon of it would weigh more than 8 billion people combined. A typical neutron star is around 1.4 times more massive than our Sun, yet it's compressed into a sphere about as wide as the island of Manhattan. Calling it dense doesn't even begin to capture the reality. In this extreme environment, a neutron star develops an exceptionally strong magnetic field, but scientists are still trying to understand exactly why. So, how does this connect to the signals we receive from pulsars? And what creates these powerful bursts of energy? To answer that, we have to look at a complex process that starts with a single particle, a lone electron, near the magnetic poles of the neutron star. This electron can get caught in the magnetic field, speeding up and producing a high-energy particle called a curvature photon. This photon then triggers a cascade, an exponentially growing shower of light and particles, all radiating outward in a mesmerizing, powerful beam. It's this beam that sweeps across space like a cosmic lighthouse, creating the signals that reach our telescopes. When an electron zips along a magnetic field line, it eventually hits a tipping point, and this marks the start of a pulse. The high-energy particle called a curvature photon moves in a straight path until the angle between its momentum and the magnetic field line becomes too wide. At this critical angle, the photon's energy disperses, feeding into the surrounding field of particles. This energy burst creates a new electron along with its antimatter twin, a positron. The electron-positron pair moves perpendicularly to the magnetic field, releasing their energy as synchrotron photons. Each of these photons can then spawn more electron-positron pairs once they, too, reach the critical angle. This process repeats in a chain reaction, exponentially generating photons and particles until the photons no longer have enough energy to keep it going. Finally, a flood of photons beams out into space, while the original electron continues along the magnetic field line, producing more curvature photons and sparking new cascades. This photon cascade is what makes a pulsar's light so intense that even from thousands of light years away, we can detect its signal. But why does this light reach us as a series of pulses instead of a continuous, steady glow? It all comes down to the alignment of the pulsar's magnetic poles. In most neutron stars, the magnetic poles, the points from which these beams of energy radiate, don't line up with the star's axis of rotation. This is a bit like Earth, where our magnetic North Pole doesn't match the geographic North Pole. Imagine a lighthouse, its beams sweeping across the dark ocean as it rotates. As the pulsar spins, it sweeps its beams across space, and if Earth happens to be in the path of these beams, we detect them as flashes or pulses of light each time the pulsar completes a rotation. These pulses are long, wavelength radio waves, so only a radio telescope can pick them up. The light produced by the cascade in a pulsar is remarkably uniform, with all the waves fluctuating in sync and aligned along a single axis, a phenomenon called polarization. This alignment is a distinctive hallmark of neutron stars, and it's precisely what we see in this mysterious 22-minute signal. But there's another twist. Within this signal, there are brief fluctuations lasting from 2 to 4 seconds, where the polarization angle suddenly shifts by 90, then snaps back. This unusual effect is yet another signature of particle cascades near the magnetic poles of pulsars. So far, much of our data seems to point to a pulsar as the source, and on the surface, it seems like an open and shut case. But there's one major problem: the rotation speed. Typically, pulsars lose energy over time as they shine their intense beams across the cosmos. This gradual energy loss causes them to slow down, eventually reaching a point where they can no longer power the particle cascades. When that happens, the pulsar fades out, entering what astronomers call the death valley, the point at which it becomes undetectable. Yet here we are, detecting this signal loud and clear, despite its incredibly slow rotation. Most known pulsars spin between 1 and 10 times per second, but this one only completes a rotation every 1,380 seconds, over 1,000 times slower than the average. This wouldn't be unusual if the pulsar were also slowing down rapidly, burning through energy to power the particle cascades necessary to produce its light. But this neutron star is astonishingly stable. showing none of the expected signs of energy loss, which defies everything we know. The astronomers who discovered the signal have considered other possible explanations. Could there be an alternate mechanism powering this neutron star's emissions? Perhaps something unknown is allowing this unusual pulsar to shine, keeping its light detectable against all odds. One possible explanation for this mysterious signal is that it might be coming from a magnetar, a type of neutron star with an extraordinarily strong magnetic field, over 10,000 times more intense than the weakest neutron star fields. Magnetars are known for their dramatic starquakes, which are powerful seismic events caused by the extreme magnetic stress on the star's crust. As a magnetar spins, the centrifugal force can make it bulge slightly in the middle. But as it gradually slows down, the star's outer crust needs to shift and realign to find a new balance, losing some of this bulge. This tension can eventually build up so much that the crust snaps into a new position, causing the magnetic fields to momentarily shift and releasing a massive burst of energy. In fact, one of the most powerful starquakes ever observed, SGR 18620 in 2004, released so much energy that if it had occurred just 10 light-years from Earth, it might have triggered a mass extinction event. If anything could reignite a dead pulsar and make it detectable, it would be something as extreme as this. So, could our 22-minute signal be coming from a magnetar that experienced a starquake? Have we finally solved the mystery of GPMJ 183910? Unfortunately, the answer is probably no. Starquakes are typically short-lived events, and while they release incredible bursts of energy, these bursts usually appear in the X-ray part of the spectrum. Yet, no X-rays have been detected from the location of this source, which is about 18,000 light-years away. Plus, it's hard to imagine a magnetic outburst lasting for 35 years. Starquakes release their energy quickly, often dissipating within just a few years. Once again, the unique features of this signal, its stability over decades, and its unusual slow rotation don't quite fit the magnetar explanation. So, if it's not a neutron star, not even an ultra-powerful magnetar, then what could possibly be generating this mysterious signal? The astronomers who made the discovery have proposed a few alternative identities for the mysterious source behind this 22-minute signal. One idea is that it could be a highly magnetic white dwarf, a type of stellar remnant left behind when a lower mass star dies. Unlike a neutron star, a white dwarf doesn't have enough mass to crush the empty space within atoms. But if it had an unusually strong magnetic field, it might still be capable of emitting radio waves. And because it's not a neutron star, it could rotate as slowly and stably as this object without losing energy over time. However, there's a catch. For a white dwarf to emit radio waves at this intensity, its magnetic field would need to be far stronger than any ever observed. Currently, we know of only one radio pulsar that is actually a white dwarf, and its emissions are about 1,000 times weaker than those of this strange 22-minute signal. If a white dwarf seems unlikely, what else could it be? Some astronomers have looked to low-frequency radio emissions from interactions between stars and their exoplanets, or from binary systems of two brown dwarfs orbiting each other. Yet, these interactions typically produce emissions that are around 100 million times weaker than our mystery signal. In the end, no existing theories can fully account for what we're observing here. While the lack of a clear answer might be frustrating, this is exactly the kind of puzzle that astrophysicists dream of solving. When we encounter new data that defies our current theories, it can lead to breakthroughs and reshape our understanding of the cosmos. This 22-minute signal has already exposed gaps in our knowledge of neutron stars, and astronomers are optimistic that similar signals might be hidden in other data we've collected from the galactic plane. These unidentified signals could hold the key to understanding processes that extend beyond the neutron star death valley, where emissions should theoretically cease. Whatever is behind this signal, we're on the brink of uncovering an entirely new phenomenon. That's all we have time for today. I hope you've enjoyed this deep dive into the mystery of the 22-minute signal. If you're fascinated by the universe's hidden secrets, please follow our podcast for more cosmic discoveries. Back in the late 1980s, astronomers first picked up a strange signal coming from a distant part of the universe. What made this discovery unique was that the signal wasn't just a random blip, it repeated like clockwork every 22 minutes. At first, scientists weren't sure if it was an error or some kind of interference. But after multiple confirmations by radio telescopes worldwide, it was clear this was a genuine, recurring radio signal from outer space. The scientific community was baffled, and they still are today. Such regularity hints at an organized source, but what could it be? Is it a natural cosmic phenomenon, or are we receiving messages from an intelligent source? To understand why this signal is so fascinating, let's talk a bit about radio waves from space. Typically, we receive all kinds of radio waves from stars, planets, and other celestial phenomena. These signals are usually random, the result of natural processes. But when scientists detect a signal that repeats in a specific pattern, it catches their attention. The universe has some predictable cycles, like pulsars that emit regular radio bursts. But a signal every 22 minutes is peculiar. It doesn't match the behavior of known cosmic bodies like pulsars or quasars. So, while many signals can be explained, this one remains a stubborn mystery. What kind of object could produce such precise regularity? So, if it's not random noise, what could explain this 22-minute signal? One theory suggests it could be a magnetar, a highly magnetized neutron star. Magnetars emit powerful bursts of energy, but usually they aren't this consistent. Another idea is that it's coming from a rotating neutron star, where unique conditions might cause it to send out regular signals. Some scientists have proposed exotic stars or other rare objects we haven't fully understood yet. But despite these ideas, none completely explain the precise timing of this signal. Natural explanations exist, but they're a bit like fitting a puzzle piece where the edges don't quite match. Now, here's where things get really exciting. If natural phenomena don't seem to fit, we have to ask, could this be an intentional signal from an intelligent source? Some scientists believe that highly advanced civilizations could use radio waves to communicate across the vastness of space. The repeating nature and long duration of this signal make it a candidate for potential extraterrestrial communication. While we have no direct evidence to confirm this, it's hard not to wonder. If someone out there was trying to get our attention, this could be their way of saying hello. Yet, this possibility raises even more questions. Why every 22 minutes? And why hasn't the signal changed over all these years? With a mystery like this, you can bet scientists aren't stopping here. In recent years, more sensitive telescopes and advanced technologies are helping us dig deeper into the origins of the 22-minute signal. Organizations worldwide are working on refining their observations and collaborating to analyze every detail. And with the upcoming launch of the Square Kilometer Array, SKA, the most powerful radio telescope array ever built, we might get answers sooner than we think. This new era of space exploration will let us peer farther and deeper into the cosmos, giving us the best shot yet at understanding this perplexing signal. But until then, the mystery continues. Could the answer be waiting out there, or are we facing a cosmic enigma that might take decades or even centuries to crack? Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers, Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blesovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.